Okay, is there anybody that did not get the tic-tac-toe active research or active information work done? Okay, you're all good. Okay, I have you on my screen. Innocent, you're 0, Collins 1, Sam is 2, Ming Kung is 3, Trevor is 4, and Matthew is 5. So here's my random number generator. 110, which is, what's 1106? Yeah, it doesn't make it, does it? Okay, let's try 011, that's 3. Okay, Sam, what'd you get for the active information?
See, I can present. Okay, can you guys see my presentation? Okay, great. I will not put it in presenter mode for fear of losing it, but so I use the Monte Carlo method to determine endogenous information. I wrote a little program that does a tic-tac-toe game. I played 1 million games. I counted ties as losses, which was one of the givens. When I did the original endogenous information, I chose the first player. The first player is determined at random, so you don't go first all the time. And so the probability of winning is around 0.4363. It is slightly less than 50% because ties count as losses. And so even though both players have an equal probability of winning, the probability of loss or probability of ties as losses brings us below 50%. So the endogenous information of this is just, the negative log is 1.2 bits of information, everything chosen at random. So I went through a bunch of different strategies. So the table is not super easy to read here. So the X's indicate if the strategy type was used, and in the opponent blocking column, if it's blank, it means the opponent did not block. If there's an X, they did block, and in parentheses is if they went first, what their starting strategy was.
Okay, let's refer to, let's see, always go first. That's you, right? That would be
yes,
you.
Yep,
okay.
That would be me always going first.
Okay.
If you always go first, probability of winning jumps to over 50%, about 58.5%. So the active information there is about 0.4 bits, just going first all the time. Next, if you always go first and you always block, your chance of winning goes up to about 79%. So that's about 0.85 bits from the original probability. Next, if you always go first, you don't block, but you start in the center, you have about a 70% chance of winning. So it's about 0.67 bits. And then here it tests out the 3 starting locations, center, corner, and side. Corner is worst, side is the worst. In fact, going on the side is worse than choosing a random location to start because it's worse than average, which makes sense. This little column here in blue or purple or whatever is the best performance that I got. That is, if you always go first, you always block, and you start in the center. So here I got about an 84% chance of winning. That's about 0.94 bits. Next is
okay, 9.4. Now is that the active information or is that the exogenous?
That is the active information.
It is.
Yes. Okay. So that's increased from the endogenous was 1.12 bits, I think. It's on the previous slide. Yeah. So it's most of the way there, but it's not. You don't have all the information out of the search. And then I did always going first in blocking with center, corner, side. Side does worse than picking a random spot because, something has to be worse than average, and picking a side spot is. Next up, always going first blocking, starting in the center, but the opponent now blocks. The opponent start location is not applicable because he never goes first because you always go first. The probability of success here is only about 7%. And so you get a negative active information here because they're now blocking and trying to win instead of not trying to win. Something that I found was interesting is between these 2 columns here. this first column is, or row, sorry, is you always go first and you block, you start in the center, and your probability of success is around 0.07. But if you do not go first, and your opponent, when he goes first, does not necessarily choose the center, your probability of winning goes up. Even though you're not going first, you have a better chance of winning than if you started in the center, because they're starting potentially not in the center. So that was an interesting result I found. And I discussed that a little bit on the next slide here. And then this is the worst combination of strategies here that I found. You do not always go first. You block, you start in the center, and your opponent blocks, and they start in the center. And that yields only a 4% chance of winning. So a little bit of discussion here. Biggest factor that I found influencing number of wins, and here ties counts as losses. So increasing the number of ties also decreases your chances of winning in most cases. So blocking results in more ties when an opponent wins when your opponent is blocking, so that's bad. If the player is blocking, that's the second biggest factor. The third biggest factor is where you start the game with. And this is the surprising result that I found, where going first and starting in the center is worse than not going first and your opponent not starting in the center. And this, the only reasoning I can think of that is, regardless of player strategies, not regardless, if somebody starts in the middle, there's a very high probability of it tying if both players are blocking. And so that would yield a smaller win percentage, but maybe a larger tie percentage.
Okay.
That's what I got.
Okay, thank you, Sam. That's very interesting. You know, in the idea of application of external information and domain expertise, I have a colleague named David Fogel. His father was Larry Fogel. Larry Fogel lived in the first wave of artificial intelligence and was a big proponent of evolutionary computing being used for everything. So in order to show this, one of the programs that David wrote was to win at Tic-Tac-Toe. And that was very early in his career. And then later he chose to do a more difficult evolutionary program that won at chess. No, I won at checkers. I'm sorry, won at checkers. In fact, he wrote a book called Blondie, Blondie. It's probably still for sale on Amazon.com, where he goes through all of the steps that he did with this evolutionary search in determining to play checkers. And then finally, in a paper which he published in the Proceedings of the IEEE, he taught a neural network how to play chess. Now, it never rose to the heights that that reinforcement learning did in Garry Kasparov's loss to chess, and it was before Garry Kasparov's loss to Deep Blue, but it was still impressive. Now, do you think that these checkers to or tic-tac-toe to checkers to chess programs evolve themselves? Can you imagine a tic-tac-toe to checkers to chess evolving itself and getting better and better? I have a problem with it. So anyway, I thought that's an interesting side note. And yeah, even David Fogel's work in training was eclipsed by Kasparov, and then later, of course, with the incredible work of OpenAI. That was the first manifestation of the winner of Go. So very interesting. Now, did anybody get any drastically different results? I know the numbers flew by a little bit quickly, but any thoughts on this?
Some different numbers, but I have some similar.
Okay, Matthew, why don't you put yours up? And
yeah. And
Sam, I didn't memorize all the numbers, but if you could look at them and comment to what you thought about it. So, I mean, Sam considered so many scenarios, so it was difficult to keep track of all the numbers for me.
Oh no, my graph's all weird now. That's unfortunate. I went through the following scenarios. One when neither knows how to block, when just player one knows how to block. And then based on that, starting at center square, corner square, and the side squares, etc. So I'm going to go over to the probabilities and see pie charts are not behaving. Here's the probability distributions of each. So this So the chance of winning I got was about 37%. And the chance of not losing about 82% on just this reference case.
Well, see, you actually looked at a different case, didn't you? Losing and not losing. I think that Sam tallied
I
all
think
of
the
it.
blue bar is what I calculated, which
Okay.
is
Right.
you have to win, which mine's within about 6% of that. So, I mean, you know,
So I did calculate the chance of winning.
Now,
but-
this is also Monte Carlo.
Sorry, like
This-
I'm
this-
calculating the whole tree.
okay, so you went and actually did a tree search.
Mhm.
Okay, so there's no Monte Carlo here. It's all this is the bottom line, isn't it?
Right.
There's nothing probabilistic about this. Okay.
So depending on how you look at playing tic-tac-toe, I thought it was important to collect both of these probabilities, winning and not losing. So here's the reference about a 37% chance to win, 82% chance to not lose. And so adding in the player one, I always put player one starting because you just take the complement of that to find the player two probabilities. If you know how to block, it boosts your chances in both regards. And then if you started in the center, it also boosts your chances. And then starting in the corner, it is actually a little bit less. Your chance of not losing is a little bit less than the starting in the center. And your chance of winning is a little less than just the average. And then of course, starting the side is worse. But the results get interesting when you add both players knowing how to block. Of course, your probability of winning goes down, but your probability of not losing is only marginally different. And starting in the center, this is something that I saw Sam just also realized, is your probability of winning actually goes down if you start at the center, but your probability of not losing goes up. And that's because just putting in the center, it can just basically gunks up the board, makes it more likely to have a draw.
Okay.
Actually, and so starting in the corner, your probability of winning goes up, but your probability of not losing goes slightly down from starting in the center. So if you're a really offensive player, then you might want to start in the corner. If you just want to play it safe, definitely start in the center. And then of course, starting in the side, the chance of winning is actually slightly higher than starting in the center. And the chance of losing is lower. So depending what you're trying to maximize here, starting in the corner or center or side could be interesting.
Okay, so you come up on a guy that's playing tic-tac-toe, and he comes up to you and he says, Matthew. I'm hearing some strange background, but I can ignore that. He says, Matthew, I need advice. I'm playing tic-tac-toe against this guy that's totally random. What do I do? What would be your advice to him?
I'd probably start in the center to see how they play. And then if you get, as you get a feel, if they're just playing randomly, then you can either start in the corners or keep staying in the center.
Yeah, the interesting thing about tic-tac-toe is that if you ever play it between two knowledgeable people, it always ends up in a tie, doesn't it? Right?
Mhm.
There's no randomness associated with it. So it always ends up in a tie if the other person is as smart as you are. even if you start in the middle and follow these different rules. But maybe for a kid who might choose a square at random, this would be important. Let me just see kind of a show of hands. How many use the tree sort of search to get the answer? Okay, yeah, okay, Colin, Matthew. And Colin, did you get about the same sort of results as this?
Yeah, it's a little hard to see like the exact numbers on my screen, but yeah, it looked about the same.
Looks about the same. How deep was the tree, by the way?
There were, the basic reference had 306,000 games total. And so some of those, of course, filling up the entire board, some of them not. But yeah, that was the highest game count.
Okay.
I
So
counted
306,000.
about 2,800 states roughly. But I accounted for the symmetries of the board as well.
Mhm. Yeah, I thought about that, but I figured I just let MATLAB do the work.
You did account for the symmetries of the board. That would throw off some of the probabilities, wouldn't it?
It actually doesn't if you do the calculation correctly.
Really? Let me think about that.
If you have to multiply by the number of symmetries there are.
Yeah. Go ahead.
The way you do it is essentially as you're searching out, you basically build up a cache of board values that you've seen before. And then essentially in order to compute, you can write the algorithm recursively, or you can do it using, computer scientists call it dynamic programming.
Yeah.
Basically, you construct a hash table that you basically stuff basically counters in each of the indices of the hash table. And every time you visit a state, you index that counter. And then in order to compute the probabilities, you traverse the whole tree and then sum up the counters.
Okay, great. So let's see, Innocent, Ming-Kun, and Trevor, did you use the Monte Carlo techniques? Okay.
I'm not sure.
You're not sure what you did?
Yeah, but because I just I'm not sure. I don't know about the algorithm, but I just divided because we have 9 steps, so I just divided all the 9 steps and then make condition for each steps.
Okay, I'm having a hard time understanding you, Ming-Kun. Your microphone isn't picking up very well. So could you get a little bit closer and say that again?
Yeah, I said, can you hear me now?
Yes, please go ahead.
Yeah, I just because I know there are 9 steps, so I just divided all the 9 steps and then consider about the conditions and then run the code. I just select like 10,000 games and then calculate the probability.
Okay, I'm not sure I understood what you did. But let me ask you, did you get about the same results as these others did, or were they drastically different?
Yeah, I think it's about the same. I get the endorsed information about 0.38. So I think
you got the endogenous information at 0.38 bits.
Yes.
Okay, I think
no. This is the probability. The probability. And
okay, so that would be 1 point something bits. Yeah.
This should be 1.4.
Okay. Okay, that's about what Sam got. Okay. Well, this was very interesting, guys. I wanted to give you something where you had to think about active information and domain expertise for a very elementary problem. And I appreciate you doing this and hope it made you think about this. Trevor, was yours about the same?
No, so my endogenous information, granted, I did do the both players at random a little differently. I didn't randomize the starting person. I just had player X, which is player 1 in my case. I just had him start every single time, and I ended up with a endogenous information value of 0.76 bits.
Okay, so if you always start and everything is random, you end up at points, what is 76 or 67?
Yes, 0.76 bits.
Okay. Wow. Which you can expect if you think about it. How many winning combinations go through the center? Four, let's see, 1, 2, 3, 4, four different winning combinations go through the center. Whereas if you have a side, there's only 2 combinations that go through that. If you have a corner, there's only 3 combinations that go through that. And so, yeah, you want to choose where most of the combinations go through. Innocent, about the same?
Yes, about the same thing Trevor got, because I didn't randomize the starting of my own game. Just player 1 gets to start all the time. So for the endogenous information, I got 0.77, which is close to what Trevor got. Yeah.
Okay. Well, thank you. Well, please take your work, and if you wouldn't mind putting it in a folder along with, if you have a presentation along with your code, and put it in box for me to take a look at. I would appreciate it. Thank you very much. Okay. Any other comments about this? Okay. Well, good. Let me go ahead and start with something else I wanted to talk about today. And many times one needs to talk about fundamental techniques in design and reasoning. And I want to do that today and show you what I think is a fundamental concept, a fundamental thing in design. So let's see, are you seeing my screen? Are you seeing my PowerPoint?
Yes.
Okay, you're seeing my PowerPoint. Okay, I want to tell you about, this is very interesting. I've had luck in my career in passing and working with and talking to some of the giants in artificial intelligence. In about a week, I'm going to go to a meeting where Carver Mead is going to be in attendance. Anybody heard of Carver Mead? No one's heard of Carver Mead. Okay. That's what happens when time passes. You just forget some of the pioneers. You probably never heard of Paul Werbos either, who was the inventor of error back propagation. And I don't know, I always find it interesting to look at the history and the contributors of technology. And even then, sometimes you know what these people did, but you don't know who they were. And it's kind of fun to find out who they were. I'm going to talk now about Combs control, a really, really smart guy. And you can see him up here in the right-hand corner. His name was Bill Combs. And he was a fellow of the Boeing Corporation when I worked at the University of Washington in Seattle. Seattle, of course, has a lot of work going on with Boeing. And as a result, he had a lot of freedom in what he did. So he was kind of an independent thinker. As far as who he was, he did turn out to be a Christian. How many know who Bill Bright is? Doesn't sound familiar? Okay. Wow, isn't that something? Bill Bright was the founder of Campus Crusade for Christ back in the 1950s. And anyway, Bill Combs became a Christian because of a meeting with Bill Bright. But he was just a wickedly smart kind of guy. He came up, when talking to him was just like a feast of creativity. He came up with all sorts of things. He knew, for example, about plasticity, about the brain. And when your brain doesn't work, if your eyes don't work, there's part of your brain that isn't in use. And so some of your other senses co-opt that part of your brain, which was normally associated with the eyes. So maybe your hearing gets better, or your smell gets better, your taste gets better. I don't know if you've heard of people entering rooms and actually clicking and finding out their location like a bat by listening to the echoes. Has anybody ever seen that? That is just a fascinating thing to observe. These people can go on to go, and they can listen to the echo and locate objects by the sound. And what is this? This is the work that is used, this is the part of the brain which was normally used for the eyes, is now co-opted to work for the sense of hearing, and your hearing is just blown away, and it just becomes incredible. So Bill had this idea, which I thought was incredible. This was, I don't know, in the 80s. He says, you know what we should do? He was thinking of the back, and he was thinking of putting this slab of kind of sensors on the back, and they would be actuators. And what would happen is there would be sound, and these actuators, maybe in a spectrogram, a very roughly sampled spectrogram or something, would react in your back. So we go boom, 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 as you heard the different things. And he says, you know, if you did this to deaf people who aren't using the part of their brain associated with hearing, they would be able to eventually associate these patterns with sound, and that would make them hear. Don't you think that is a cool idea? Yeah, it's a wonderfully cool idea. So we actually looked around see if anybody was interested in developing this, and nothing happened. And then, as happened, a number of years later, somebody came out and figured out how to do this, and they did do the thing in the back. But then somebody else recognized, you know, your density of nerves on your back is not as dense as some other places on your body. And you know where the most dense collection of your nerves is on your body, on your outside?
Is it your tongue?
It's your tongue. You have more nerves per square inch, more sensors per square inch on your tongue. And so I was introduced to a neurosurgeon named Yuri Danilov, who did incredible work where he put this array of sensors, not on the back, but on the tongue. And by putting this on the tongue and then hooking it up to a microphone and having a translation of this audio signal to a signal on the tongue. Oh, I'm sorry. No, it wasn't audio. Okay, backtrack. It was literally for blind people. They would take a camera and they would put this really rough version of this camera on the tongue, and they could teach people to see with their tongues, of all places, because again, the eyes weren't being used, and so that part of the brain was free to go other places. And one of the greatest successes he had was with this very athletic guy that did mountain climbing. And there's videos that show him with this tongue thing in that he could do things like he could play catch. He could play catch with his, I forget who it was, his brother or his son or something like that. But he could play catch and actually move small objects around the table. And one of the things that Yuri Danilov said about this incredible experience is that that this blind person actually developed the ability to, with this rudimentary image on his tongue, to have depth perception, which really surprised me. And he said there's no physiological reason that could happen. But anyway, Bill Combs was way before the curve in doing this sort of thing. And he also came up with something called disjunctive Combs reasoning, which was taking a concept which I want to explore now. And it's how to design things. And we're going to look at a specific case of fuzzy logic because that's where he applied it. But it's more general than that. So this is so-called disjunctive Combs reasoning by Bill Combs. We did become pretty good friends and hung out together. And he was, I'm not sure. But unfortunately, I've lost contact with him. Okay, conjunctively tightly linked control. Okay, on the top here is the equation that we use in so-called Mamdani control. And I'm going to present this from the idea of fuzzy logic, but then we're going to generalize it a little bit. And that is the intersection of a bunch of antecedents that give a certain consequent. And when you set up your rule table for fuzzy logic, this is the result, that this is the logic that you use. This is so-called Mamdani control. For example, if you have a consequent of turning right and you're in a car, you can use the following rule table. If the first antecedent, turn the front tires slightly right, and if you want to turn right, turn the rear tires slightly left, and lightly brake the right tires, and slightly accelerate the left tires. So what you can do is assign a weight, if you will, to all of these in order to turn the car right. Now, if you're like me, if you want to turn the car, you turn the steering wheel, so you're turning the front tires slightly right if you have a car that steers from the front. But in general, this is the sort of thing that you could do for a vehicle that you wanted to turn right. Now notice these are all connected by a conjunctive and. When you say conjunctive, think of conjoined. Okay, conjoined, they're joined close together. And when they're conjoined close together, it's conjunctive. And ands kind of link things together because in order to be totally true, this has to be true, and this has to be true, and this has to be true, and this has to be true. And if you break one of those and one of those is false, then in a Boolean sense, your entire statement is false, right? So and statements or conjunctive statements are really, really tightly connected. Now let's look at Colmes's idea of okay, well, I guess we're still on conjunctive control. And I wanted to point out here the number of rules. Do you remember we said that in the rule table for Mamdani control, if you have 2 antecedents, you had a square. If you had 3, you had a cube. And so you had a kind of a curse of dimensionality here. As the number of antecedents increased, the number of rules that you had to fill in increased explosively, if you recall that. So with Mamdani fuzzy rules, if you had L antecedents and each one was an N fuzzy partitions, you know, if you had, for example, a speed and your fuzzy partition was, well, say for acceleration, decelerate, don't accelerate, accelerate. You would have 3 fuzzy partitions. That's what I mean by the fuzzy partition. So you can have more or less if you want to. But anyway, in that case, that hypercube that you get in all of these dimensions and L dimensions would require n to the Lth rules. So that's one of the problems with conjunctive tightly linked reasoning. Holmes noticed that there is something similar called disjunctive loosely linked reasoning. Notice that each one of these antecedents that I gave you was capable of turning the car right by itself, right? So if you want to turn right, you can turn the front tires slightly right, then you turn right. Or you can turn the rear tires slightly left, then you turn right. Or you can lightly brake the right tires and you turn right. Or you could slightly accelerate the left tires and turn right. You notice the big difference here is that we have the ors connecting all of these things because of kind of an inherent redundancy that you have in the system. And so this is disjunctive, or we'll see loosely linked reasoning. And with the Colmes fuzzy rules, if you have L antecedents, you have N fuzzy partitions. Then because of this or, you only have L times N rules. So with Mamdani, your number of rules increases exponentially. For Colmes control, it increases linearly. Now, there's 2 equations that we've seen. The one on the left, whoops, there it is. The one on the left, or the first one for Mamdani was the equation on the left, which was Mamdani, was the intersection. If this and this and this, then the consequent. Whereas on the right, if you have an antecedent, if this, then the consequent, or if this, then the consequent, or if this, then the consequent. This is called the law of importation. And fascinatingly, in the Boolean sense, there's an equality sign here. Both of these laws are identical in the world of Boolean, not necessarily in the world of fuzzy, but in the world of Boolean, they are identical. Now, you look at it and you think of the two things, it isn't obvious that they are identical. I am going to ask you as a homework problem to prove that this is indeed true in a Boolean sense. And so you think that if it's true in a Boolean sense, it might be able to be generalized very nice to a fuzzy sense. And that's indeed what Combs did in his Combs reasoning. Now, here is a general statement. This is not only true for fuzzy control, but it's true for design in general. And we're going to look at a number of these different results. Number one is scalability right here. Now, scalability, we've already seen that the conjunctive reasoning or the Mamdani control increases exponentially where the disjunctive reasoning increases linearly. That's very, very good. The Mamdani control is very rigid. It's very brittle. In other words, you have to have this and this and this and this. In a Boolean sense, if you have this and this and this and this, and one of those is zero, then the whole statement is zero, right? In order to get the whole statement to be true, you have to have every one of the elements present. So this is important. For example, if you have a design in a system which requires a conjunctive synthesis of a number of components, and one of those components breaks, then your whole system breaks, right? Your whole system breaks because of the and. For the disjunctive case, that isn't true. Let's revisit this. This is the or, okay? If you turn the front wires slightly right, then you turn right. Well, suppose your brake on your right tire fails. Let's go back up here. If the brake on your right tire fails, you won't know what to do. It doesn't. If your brake on your right tire fails, you won't know what to do because your rules say that all of these conditions have to be in play, and you weigh them up and you put them together into a final consequent. So this is very brittle. If one of these fails, then the whole thing fails. Whereas with the disjunctive or the lightly case, if your brakes on your right tire fail, then you can still turn right because you have this kind of, if you will, a redundancy in here. You can still turn slightly right by using your front tires or your rear tires slightly left or slightly accelerate the left tires. So therefore, it is less brittle. Now, where does this occur? This occurs, for example, in swarm intelligence. Swarm intelligence, you have very specific disjunctive reasoning because you have a lot of independent ants. So ant 1 says build the anthill. Ant 2 says build the anthill. Ant 3 says build the anthill. Ant 4 says build the anthill. And they're all connected by ors. And if you go in and you kill a lot of those ants, you still have a bunch of other ants that are saying, Ant 1 build the anthill, or Ant 17 build the anthill, or Ant 52 build the anthill. It's very disjunctive, and it has an incredible plasticity, and it has a great ability to withstand challenges. The coupling is high, and in fact, this is kind of the takeaway for the general idea of design. When you design something, if you design something with a lot of interconnected parts, then that is kind of a conjunctive design. Whereas if, to the degree allowed, and it's not always allowed, but to the degree allowed, if you do a design in different modular parts and then combine those together, you will get a more of a disjunctive or a high tolerant sort of system, one which is more fault tolerant. The robustness is low. This goes back to the rigidity. Robustness is low. If you lose one of them, yeah, the whole thing goes down. Like with swarms, you have a high robustness. Same thing with the fault tolerance. A lot of these are related to each other. You can have if you have something which is faulty in your design, then the whole system fails, right? Like your starter or your starter is needed to run your car. And if your starter fails, the whole thing fails, right? Because they are conjunctively interconnected. And by necessity, by the way, often you don't have the ability to choose the degree of conjunctiveness or disjunctiveness. But if you do have the ability to separate things, then that's a heck of a lot better. One of the classic examples of this is the Aegis system, which is used by the United States Navy on some of their ships. The Aegis system has been described as a tiger on a leash. It is an enormously powerful weapon system, but very intelligently, what the Navy does is they have designed the Aegis in a bunch of disjunctive components. So you have, I'll describe it very generically, you have weapons A, weapon B, weapon C, weapon D. And what happens is that the commander can come and for a certain scenario said, I want weapons A, E, and F. In other words, he's able to choose from a smorgasbord of different options and take advantage of that disjunctive relationship. In fact, some of the scenarios are so common that there's a code book that they use on Aegis. So they get a certain scenario and they look it up and they say, okay, in this scenario, we use system 3, 4, and 8. And so they know what to do. So the commander doesn't even have to think. So that's very interesting, and also attests to the robustness and the plasticity of what happens. Cognitive parallel. For low order systems, CR most closely parallels human cognitive inference. Now, what do I mean by that? Well, suppose that you're asking somebody in the stock market, and they consider three things. They consider two things, maybe the S&P 500 and the Dow. So they look at it and they can do a little table. You know, if the S&P loses, stays the same, or gets high, same thing for the Dow. And then they can have different reasons in their rule table finally tessellated in order to do that. But when the system becomes very complicated and we have, maybe 25 different indices that we're trying to keep a hold of, the Dow, NASDAQ, the S&P 500, what is that, 5,000, the Russell 5,000. So we're doing a bunch of these. People cannot think in that high a dimension. So rather they begin to think more disjunctively. And they think, well, if the Russell goes up and the Dow goes down and the blah, blah, and the S&P goes down, and they begin to think disjunctively, not looking at the interactions of the two. So I maintain that for complex systems, the disjunctive reasoning mostly parallels human cognition for complex things. For simple things, we think conjunctively because we have the ability to do that. Yeah, and then the last one, parallel and distributed processing ability. I'm going to skip that because I'm not ready to yap about it. Let me give you an example of a very interesting phenomena which happens. Okay, before I go into the next thing, the takeaway here is that in the design, in any design that you can do, if you have the option between a conjunctive or a tightly coupled system or a disjunctive sort of system, you choose the disjunctive. Now, I know many of you are really into writing code. I am probably not as talented as most of you in writing code. And when I used to write code, I used to write and write and write and write. And I get so far down, I'd forget what I did in the beginning, and the whole thing kind of fell apart. It was just, everything was too tightly coupled. Rather, isn't it much easier to write code in modules, right? to write a specific sort of function, then to write another function, then to write another function, and then loosely couple them in some sort of fashion. So even in writing software, the conjunctive sort of way of doing things emerges because you get confused otherwise, or at least I get confused. And I found out that writing them modularly is much more effective, and I can keep a lot more balls in the air than I can by a conjunctive big attempt at doing the computer programming. Anybody else think of an example where this is true? I want to see if I'm communicating this idea.
Perhaps problem solving, or it's a little bit like that programming.
Okay, problem solving in what sense?
Like breaking problems into separate things and addressing
Oh,
each one on
that's
the
an
basic level
interesting.
individually.
Yeah, if you can take a big problem and break it into a lot of little problems, it's a lot more easy to solve. That's okay. Yeah, that makes sense. Any other thoughts? I drank a whole cup of coffee while I was waiting for Matthew's response, and I don't have any more coffee. So you're going to have to speak up if you want to, if you have an idea. Okay, so it's just a general rule of thumb. I don't know if this is ever taught in engineering design, and it certainly is something that should be as a general philosophy. There's implications, for example, in AI ethics and complicated AI. In fact, Sam and I wrote a paper which is going to appear in the transactions on IEEE transactions on systems ban on cybernetics, which looked at the consequences of this for artificial general intelligence. Now, the problem with the situation is that simple artificial intelligence has really made great inroads. And most of the successful systems that have been reduced to practice are very simple sort of artificial intelligence. If one begins to get complicated, now what do I mean by complicated? I mean something like self-driving cars. That's much more complicated than some of these artificial intelligence programs. Driving artificial in car becomes complicated because you have a lot of sensors and you got a lot of things working on. And as things become more and more complex, and they are kept together conjunctively by very loosely interconnected sort of ideas, then the more applicable they are, or the more prone they are to failure, to having unintended contingencies. And it's harder to keep track of the total design. And for self-driving cars, for example, you used to have windblown plastic bags recognized as deer, or even a plastic bag in the side of the road thought to be a rock. And yeah, you can fix these sort of things and they're not serious, but also you have collisions of systems. You remember that Uber self-driving car that killed a pedestrian, I don't know, what is it, 2-3 years ago right now? And, you know, it was just tragic, but that was literally a conflict between two of the sensing systems and the processes that were going on. And expert engineers that looked at the case said there's no way that that pedestrian should have been killed. But because of this confusion, which was brought on by the two sensors, I think it was a LiDAR and some other system, that they collided together, and because of their confusion as to what to do, they didn't know what to do. They didn't do anything, and they end up killing this poor lady pedestrian. And again, this is the result of conjunctive reasoning. So what does this do for artificial general intelligence? It tells you that, well, you got to be careful if you're going to design artificial general intelligence. The best way maybe you can do it is to design little pockets of simple intelligence and then connect them in some way. That would be the disjunctive sort of way of doing that, as opposed to trying to take just one big effort at artificial general intelligence. So And I think you know from the beginning of the course, I don't believe that artificial general intelligence is possible. I think artificial intelligence is going to become more and more powerful, but it will never replicate what we do. Okay, so this is conjunctive and disjunctive reasoning. And here is, I think, a very interesting example of what happens to fuzzification if you have a disjunctive system. Now, here's what it boils down to. What it boils down to is that you usually have an input, which the input I'll call S sub k, okay? And you're going to have a output, which we're going to call the consequent of C sub k. Now, how do we get that with Mamdani control? We have to go through fuzzification, turn the crank, and then do defuzzification, right? It turns out that with fuzzy Combs control, that the mathematics for fuzzy Combs control boils down to a simple actuator. In other words, it's a function that if you give me the input, I don't have to do fuzzification and defuzzification. I can literally take and just read off what the corresponding consequent is going to be. And this can be derived from the individual fuzzy membership functions. So let me give you an idea here. This is from a figure caption. We're going to have the fuzzy rules. N implies large. So if you have N, it's going to imply large here. We're going to have 0 imply medium. And we're going to have P positive imply small. So this is almost a kind of inverse sort of relationship. So what do we do in such cases in kind of fuzzification? Well, we have an observation. Here the observation is -2. And what this -2 does is it tells us, okay, on this first fuzzy membership function of 0, it's going to give us this much. I'm sorry, that's the second fuzzy membership function. This is the first fuzzy membership function. It gives us this value. So therefore, on the N and the Z plots over here, we get 2 numbers. Now for the P, it's 0, so we don't even weight that, right? Now you remember with the fuzzification, what do? We take this number, and we weight this membership function, if you recall. So we take this number and we weight this membership function. So this no longer goes up to 1, it goes down to whatever the value is there. In a similar fashion, we take this number and we weight the middle membership function, and this is going to be a little bit smaller. And the other membership function doesn't even come into play, does it? So we add these 2 up, we add up this curve, and then we take the center of balance. Remember, that's the center of mass that we did for the defuzzification. Well, the interesting thing about this is that as you slide this antecedent across the possible values, each value gives you a number. Each value gives you a number, and this is the defuzzification. So this value is going to give you a number. This value is going to give you another number. So each value is going to give you another number, and you can go through this process and look at the mapping of all these numbers and just say, okay, this is the result that we get. This is the mapping of the consequent to the if you will, the sensor input to the value of the consequent, and that's all you have to do. So it all boils down to, interestingly, a simple actuator sort of number. Okay. So if you're interested in finding out more about this, I put a little link to a paper here. And the paper goes more into application of this in Combs control. In fact, we just have a little bit of time here, so let me see if I can, well, what did I do there? I have no idea what I did. So are there any questions on that at all? Okay. Interesting, different philosophy. I think it has some specific applications, and it has some very general sort of applications in design philosophy. One of the big things that happens in AI is something called AI ethics, and you've all heard of ethics. There's two types of ethics that I'm aware of. This is the way that I look at it. There's design ethics. Design ethics says that you want to make sure that whatever AI or whatever system in general you design does what it's supposed to do and does no more. That's design ethics. It does what it's supposed to do and no more. And Dr. Rivas, who is on the computer science department, sits on the IEEE standards board that is drafting some of these ideas for artificial intelligence ethics. But it seems to me that designing something so that it does what it's designed to do and no more, that's probably good for all engineering design, right? And how do you determine, how do you assure that you design something that does what it's supposed to do and no more? I think, first of all, we have to have design expertise, right? So you go in with the design expertise in order to design that. Remember WD-40 or Formula 409, right? And the fact that if this domain expertise was missing, nothing would happen. We have something which is similar here. We have to go in with design expertise. Then we need to test it. We need to test it in the field, because there could be things in the field which the designer did not consider. I'm sure that the designers of these early self-driving cars did not appreciate wind-blown bags. They didn't recognize this, okay? They didn't think about it. So they put it out in the field and they said, whoa, we got a problem here. Same thing with the, with the Uber car, the Uber self-driving car that killed the pedestrian. We didn't know that these subsystems would collide and result into the death of the system. And so those tests must be put together. Now, I have heard, and I like your opinion on this, I have heard some people say, we don't need all the expense of going out and testing AI in the field. Rather, we can write computer programs to test the AI under different scenarios. Anybody have any reaction to that?
It
Sounds
seems
a little
like
circular.
Circular in what sense?
Well, if you had good AI to test your AI, you wouldn't need to test your AI because you already had good AI.
Okay. Matthew, you were going to say something.
it seems like it could be useful for a little bit, but it's not comprehensive.
It's not comprehensive. For example, in the test driving of the self-driving car, do you think they'd ever put wind-blown bags in that computer-generated testing? No, because they would have never thought about it. That's the reason you have to go out in the field and test it. And when are you sure? Are you ever going to be 100% sure about any design you do as an engineer? So what's the criterion? Anybody have any idea? You're never going to be 100% sure.
So if we're talking about like sort of formal computer code, there are some methods of actually formally proving properties of certain programs. But it,
yes, you can.
Sort of the class of those programs is severely restricted.
Yeah, you know who Donald Knuth is, right? He said something which was kind of famous. He says, I have written the computer code. It does exactly what I want it to do, but I have no idea how it'll work. In other words, yes, you can look at computer code. You can go through the diagnostics and make sure that computer code does exactly what you want. But eventually it's going to apply to the real world. And the question is, are there contingencies which you haven't thought of? So I agree with you, Colin, that we can test computer programs in order to assess their validity. But I think, as Donald Knuth said, he really wasn't sure how it would work. He knew that that computer program did exactly what he wanted it to do. But what were the consequences of him wanting to do exactly what the computer code said? Well, I'll tell you my parlance. We use this in jury trials. And when somebody comes up for murder and you're on the jury and you hear all the evidence, what's the criteria that you use in order, if you want to find the person guilty? Do you know the legal parlance for that? If you watched any TV, you know.
Beyond reasonable doubt.
Beyond reasonable doubt. So it seems to me that that's what we want to do in terms of verifying the validity of a design. Now, all of a sudden, you're confronted with the question: how do we measure that? I mean, in legal parlance, it's kind of a fuzzy idea, isn't it? Beyond a reasonable doubt. In fact, you have split juries, so they come down on different fuzzy membership functions on the guilty or not guilty. But nevertheless, that seems to be a useful starting point for design ethics, be it AI or anything, is that works exactly as it was designed to work and does nothing else. Okay. Is that always applicable? I can see that applicable in cases where the AI or any of the design that you're using involves life and death. What about Alexa? Have anybody used Alexa? You know that is so. I don't know that one. Did you hear that? Did you, Alexa? Tell us a joke.
What did the stuffing say to the turkey? I'm so into you.
I'm what? I didn't hear what it said. What did the turkey say to the stuffing? I'm so into you.
So into you.
Okay. I got it. Okay. So that was bad. But you ask it different things, like, for example, Alexa, play Meatloaf, I'll Do Anything for Love.
I'd do anything for love, but I won't do that. Single edit by Meatloaf from Spotify.
Alexa, stop. Alexa, play Get a Job by the
Silhouettes from Spotify.
It's improved. Okay, Alexa, stop. It used to be I would ask those questions and I would get, I'll Do Anything for Love by Jay and the Buttoneers. Yeah, just a band from left field. So should Alexa be, Alexa, I'm going to turn you off. Because you're problematic. Okay, Alexa's now turned off. I put her in the corner to punish her. Now, should Alexa be required to work beyond a reasonable doubt? It clearly doesn't, does it, if you've ever used it? So what we should apply here, I think we should apply something which is closer to civil law. Do you know what happens if you go to the civil court? What you have to do, it's not evidence beyond a reasonable doubt, it's some other type of evidence. You guys got to catch up on this.
Beyond a shadow of a doubt?
No. What's the difference between a shadow of a doubt and, I don't know. It's the preponderance of evidence. Therefore, if in a criminal trial, it has to be beyond all reasonable doubt. So that's like 95, 99% sure, you got to be sure. But in a civil trial, it's a preponderance of evidence, which is 51%. If you're 51% sure, then the preponderance of evidence says, yeah, that's going to be okay. So for the design ethics, I suspect that the preponderance of evidence would be enough to pass that. There is no life-threatening, well, there's no immediately, you could come up with scenarios all over the place, but there's no life-threatening consequences which come from the use of Alexa, right? I'm sure there probably is, but I can't think about it. So these are the sorts of things that need to be applied to design ethics. And I think what the thing that we wanted to show today was that in general, one of the things that should be considered in the design of anything is this disjunctive versus conjunctive sort of way of design. It has so many more different, it has so many wonderful attributes. The problem is you might be presented with a design problem which you cannot use the disjunctive sort of way of doing things. It just might not be possible. But if you do have that option, yeah, make it simple. You've heard the KISS, right? Keep it simple. What's the last word? Stupid.
Silly.
Silly. Keep it simple, silly. Okay, something like that.
That's
Okay,
a nice way of saying it.
it is. So okay, one other thing I wanted to do. Any questions or comments on that before I dazzle you with
I have just a quick question about the conjunctive versus disjunctive.
sure.
If your consequence is do something versus don't do something, I'm a little bit confused as to sort of what the difference between those two would be. Like if you can sort of negate the antecedents and negate the consequent, are those two sort of equivalents in a sense?
Well, I guess your question kind of pre-assumes a Boolean sort of thing. I think in general, what we do in any detection theory where you're defining yes versus no is always fuzzy. You have to design a threshold in order to figure out the trade-off between the two. I don't know if this is what you were referring to, but in any decision problem, you have your false alarms versus your detection probability. And invariably one goes up with the other one and you can't avoid it. And you just decide how much you decide how valuable is a false alarm, how valuable a detection theory is, recognize the consequent and go with it. I don't know, the DoD, the American military, has something called CFAR radar. Have anybody heard of CFAR radar? CFAR stands for Constant False Alarm Radar. They want to keep their false alarms at below a threshold. And that can really screw up the detection probability in some cases. If you got a lot of noise and you want to keep the false alarms down, then the detection probability is also going to go down. But that's what's important to them, is the constant false alarm rate. I don't know if that addressed your question though, Colin.
Yeah, so in the fuzzy world, is there some interpolation that sort of lets you pick what point you want sort of on the ROC curve of, I want.
Sure. In fact, that's true of all decisions. That's true of all decisions. Let's see. Did I go through the ROC curve in here? The idea that you have a balance between your detection probability and your false alarm. And you want a high detection probability, but you want low false alarms. So you have a little black box, and this little black box has a little light on it that lights up if you're being attacked by enemy missiles, okay? And that light isn't on if you're not being attacked by enemy missiles. How can you be assured of 0 false alarms? Always leave the light off. If you always leave the light off, you get 0 false alarms. Good job. What's that do to your detection probability? Right? Suppose that you want 100% detection probability. You always leave the light on, right? So those are the two extremes. Anything else goes between these extremes. And you have to balance the two off. I think I mentioned Charlie's Fish Market in here. You would remember that. When I was when I was a disc jockey, the Charlie's Fish Market wrote their own copy, and their copy came in, and Charlie's Fish Market, it says, here's the copy we want for our 15-second ad, is that good meat ain't cheap, cheap meat ain't good, so eat fish. That was their little short advertisement. So what they're saying is that the better the meat is, the more it's going to cost, right? There's a trade-off here. If you think about the trade-off, let's say we have safe cars versus expensive cars, right? The safer a car is, the more expensive it's going to be. You want a totally safe car, get yourself an armor-plated Humvee, right? If you want a cheap car, a cheap mode of transportation, get yourself a scooter. Now, scooters aren't safe, and armored Humvees aren't cheap. So there is a trade-off as we go up in expense, and you can think of every expense having a maximum degree of safety. Let's suppose that we can measure safety. So as the price begins to go up, the vehicle becomes safer and safer and safer, right? And that's referred to as a Pareto Frontier. And this is a place in engineering design that we don't have an idea what an optimum is. There is no optimum. It depends on what you want to do. And so if I only considered price and safety, I would probably go up to how much price I could afford. Then I would work my way up and find out the most safe car that I could buy, right? So that would be my decision on that Pareto front. So a Pareto front is an example of where there is no optimal solution, but there's a whole gradient of solutions, which depends on what the human wants. Like if I wanted to be attacked by thermonuclear missiles, I wanted to know, I would want a high detection probability, right? So I wouldn't mind a few false alarms. I could check out the false alarms, but I would want a high detection probability. And I'm sure that there's cases where I don't want any false alarms either. So it depends. And in engineering design, we're always confronted with this trade-off, and we have to make the decision of where on this Pareto front or this frontier front where we do make the decision. I don't know if that answered the question any better, Colin.
It did, thanks.
Okay, excellent. Now I have 1 minute left, so I'm going to try to share. You know what? Well, no, I think I better share it. This is Thursday, right? Okay, and when do we meet next? On Saturday, right? That's a joke. No, we're not meeting on Saturday. We're meeting on next Tuesday. Okay, I wanted to share with you some things that I put on our sacred spreadsheet. Okay, so can everybody see the spreadsheet? Thumbs up. Do you see a spreadsheet? No?
I can only see part of it. Oh, there it goes.
Okay, it took a little while. Okay. Yeah, a couple of things. I do have I want you to do something. And see, this is going to be more difficult for some of you than other people. But I would like you to use a resource such as TensorFlow or PyTorch to implement a convolutional neural network. Now, this could be an autoencoder, a classifier, a GAN, anything you want to. And if you're new to this sort of thing, then you go ahead and choose a more simple problem. But I prefer you not just regurgitate something somebody else has done. Please don't do that. Do something no one has done before. If you use a CAN software that somebody has trained on data X, don't use data X, use something else and do something which gives you some information as to what happens. If you would rather do another project other than this, let me know. I'm certainly open to that. I have put in here Dr. Bowie's slides about the web resources, and you can download that from here. That's his PowerPoint presentation. And so that is well and good, as well as I put Glauco Amigo's PowerPoint presentation here on the GANs. I have yet to get from Adam, and it's my fault. I think he sent it to me. I think I lost it. His work on simulated annealing, but that would be something else that you could do if you could come up with an interesting problem. And I'd like to have these due in November 20th in class. So if you have questions on this, just please pop me an email and I'll give you my opinion. but don't do something simple. Don't do something that just lets you get by. I'm counting on you to push yourself. We're all graduate students. You're all professionals. You have your degrees. Do something which makes you learn. And then I do have some homework to do, and I haven't decided the date yet. It won't be next time, but I would like you to prove the law of importation in Boolean logic. That equivalence in a Boolean sense between disjunctive and conjunctive sort of reasoning. This corresponds to just generating some truth tables. And are you familiar with the truth table for implication? Okay, so that's what you do. And then I'd like you to think deeper about it. It turns out that conjunctive control has a lot more knobs to turn than disjunctive control, right? You got to fill up this n to the L rules in this hypercube for the conjunctive, whereas for the disjunctive, you just have things growing linearly. Doesn't it make sense that there's maybe something that conjunctive can do that disjunctive can't do? Yeah, you have more degrees of freedom in the conjunctive. And even though it equates in the Boolean sense, it just doesn't make sense in the fuzzy sense where you have lots of knobs to turn or a few knobs to turn, that they should be equivalent. And I'd like you to think and see if you can come up with any ideas on maybe something you can do in fuzzy control. Now, something that you can do in conjunctive reasoning that you might not be able to do using disjunctive reasoning. Now, another thing, there will be no class on Tuesday the 9th and Thursday the 11th. I'm going to ask that you watch, if you haven't watched it already, Bernie Woodrow in the 1960s. This goes back to the beginning of this class where we tried to paint some of the history of artificial intelligence. And I think you'll be surprised, number one, of how crude the recording is of Bernie Woodrow, but also be amazed at some of the things that he did with his simple add-a-line. And his add-a-line was a neural network with no hidden layers that he was able to train using steepest descent. And in fact, that used to be called the Woodrow-Hoff algorithm after Bernie Woodrow and his graduate student Hoff. I don't know who Hoff was. And then we talked about Paul Werbos, the inventor of error backpropagation. So I'd like you to listen to an interview. It's very rare that we get, I think, kind of a legend that has really made a monumental breakthrough in mathematics that has just had widespread ramifications. We have lots and lots of papers today, and we get excited because these papers come out and we say, ooh, this is the newest, greatest thing. But you wait a couple of years down the road and I don't know, they kind of fade into the, I don't know, wherever things fade. And Paul Werbos's work hasn't. In his 1970, I don't know, it depends when he did a lot of work before his dissertation, but his dissertation published in 75 is very interesting. I want you to notice that he interacted with people like Marvin Minsky. Anybody heard of Marvin Minsky? Okay, Colin has. Marvin Minsky is the founder of the MIT AI lab. I probably don't have the name exactly right. And he was, some consider the father of artificial intelligence at MIT. And Paul Werbos did interesting interactions with Marvin Minsky. And he talks about his interactions with Marvin Minsky. Now, Marvin Minsky turned out to be a hater of neural networks. He didn't like it. He liked his rule-based systems. And even though Paul Werbos was able to talk to him in a friendly fashion, it's a very, very interesting historical consequence. He also talks about Alonzo Church. I'm not sure if you know Alonzo Church, but when Alan Turing came to the United States, he worked with Alonzo Church and did some important work together. In fact, Alonzo Church, I think, Colin, you mentioned, you know this, he came up with something called lambda calculus and as a computing model. And Turing, of course, had the Turing machine, and they worked together and they figured, you know what, these two things can do exactly the same thing. And together they came up with the Church-Turing thesis, which is that all computers can basically be any operation on any computer today could be done on a Turing machine. Turing's 1933 with 30 something Turing machine, because Turing machine was, so powerful. Now on the Turing machine, it might take 1 billion or 1 trillion times as long, but nevertheless, computationally, you could do the same thing. That's known as the Church-Turing thesis. And that means that if we find any limitations on the Turing machine back then, computationally, those same limitations are applicable today. It's by the Church-Turing thesis. But Paul Werbos did some work with Alonzo Church also. So I think you'll, I hope you enjoy it. And then we'll gather again on Tuesday, November 16th. Okay. Any questions at all? We've really run over, and I apologize. No, I don't apologize. I did the best I could. Any outgoing questions? Okay, I drink a half a cup. Half a cup of silence is enough. So take care, be of good cheer. Bye-bye.
Dr. Marks?